Today I'm going to talk about a really interesting piece of chemistry research that flips a common assumption in materials science. We usually think that the best materials are the ones without imperfections, but the article I chose shows the opposite, that adding engineered defects into graphene can actually make it work better. I'll explain what the researchers discovered, why the results matter, and how this connects to a broader shift happening in modern chemistry. Before getting into the study, it helps to know what graphene is. Graphene is a single layer of carbon atoms arranged in a hexagonal pattern. It's often called a wonder material because it's extremely strong, very conductive, and incredibly thin. In almost all research, the goal is to make graphene as perfect and uniform as possible. So, the idea of intentionally adding imperfections goes against the traditional approach. The article describes research where scientists use a molecule called azopyrene while growing graphene. This molecule disrupts the normal arrangement of carbon atoms. Instead of forming only perfect six-membered rings, the graphene developed controlled irregularities called 5 to 7 ring defects. What makes this study different is that the defects weren't accidental. The researchers designed them on purpose as part of a new materials engineering strategy. These defects aren't cracks or damages. They're simply different ring patterns within the carbon sheet. Normally, graphene is made of 6-member rings, but the researchers created 5 and 7-member rings. These subtle changes in structure end up changing how electrons move through the material. They also make graphene more chemically reactive, which is useful for many applications. This is surprising because in most areas of material science, defects are considered flaws. They usually weaken materials or make them less efficient, but in this case, the defects actually improve performance. This challenges the long-held belief that perfect materials are always better. It opens the door for a new strategy called defect engineering, intentionally designing imperfections to get better results. The engineered defects give graphene several enhanced properties. It becomes more electronically versatile, more magnetic, and more chemically reactive. These features make it useful for things like sensors, catalysts for chemical reactions, and possibly even next-generation electronics and energy storage devices. So, the practical impact of this research could be very broad, affecting several different technologies. This study also fits into a larger trend in modern chemistry. A second article I looked at from the University of Hawaii describes a method where chemists use light and a catalyst to transform simple aldehydes into more complex molecules. Both studies show chemistry shifting towards smarter, more intentional design. Instead of following old assumptions like materials needed to be perfect or reactions needing harsh conditions, researchers are finding creative, efficient ways to improve performance. This research matters because it shows how material properties can be tuned with precision. It could lead to more efficient electronics, better catalysts for sustainable energy, and highly sensitive detectors for environmental or medical use. It also reduces the need to create entirely new materials from scratch. Instead, scientists can redesign existing materials like graphene to make them more effective. I found this article interesting because it challenges the assumptions that imperfections are always bad. It shows how creativity in chemistry can lead to unexpected discoveries. I also like that something at the atomic level, tiny changes in a carbon pattern, can have such a big impact on technology we might use in the future. To sum it up, the researchers showed that intentionally adding defects into graphene can improve its properties in useful ways. This discovery opens new paths for materials design and supports a broader trend towards innovative, efficient chemistry. It also reminds us that scientific progress often comes from rethinking what we assume to be true. Thank you.